Yeah, thank you, Martin. It's really great to be here, actually. I done this talk maybe 3 or 4 months ago in Leeds, but it's not the same, really. I mean, speaking in front of your home community, it's a lot. You feel it's a lot safer environment, and it feels really good. So I'm really thankful to be here. I want to start by saying basically thank you to you lot for coming out. Also thank you to Martin, Colin, and Sam for inviting me. Frontend NE it's sort of taken off like crazy amount. I tried to do this maybe 3 or 4 years ago and completely failed. No one was interested, whereas these 3 guys have put in so much effort, and it's turned into an amazing event. So I want to start with a round of applause for these guys, because they really do deserve it, because it's actually a really, really great event, and I think it's the best event in the Northeast at the moment. So round of applause, please. So actually, I just want to start on a low point, unfortunately. I've got a bit of a thing. I want to tell you, basically want to tell you something, and you're not going to like it, but this number represents the number of Star Wars movies I've ever seen. Yeah, I mean, I haven't come out with my parents yet, but it's not great. So if anybody was expecting any sort of Star Wars related sort of gags, it's not going to happen. Somebody put Kenobi in my description. I don't even know what Kenobi is, so it's not any use to me. Now this word is, I sort of hate this word, but you're going to hear a lot when it comes to rendering performance. How many of you put your hands up if you actually got the reference to the first slide in the sort of yeah, I don't know. I feel quite old. I'm quite young, right? So that's not good. So it was Blankety Blank, some weird show with Paul O'Grady dressed up as a woman. But yeah, I try to play on that. And this word, when it comes to rendering performance, you will hear this word quite a lot. And I want to go over it briefly in terms of actually what it actually means. So we've all viewed sites, we've done various interactions, we've scrolled a site, and you may have come across a time when you've scrolled a site or you've done a certain animation. Maybe you've used jQuery to do like a slide down event, and you've noticed that there's a judder. So Jank is actually the word to use for that. I'm going to say it's judder because Jank, with regards to my accent, Jank doesn't sound good. So I'm going to try and stay away from it as much as possible. But there's also something known as checkerboarding, which is another term when it comes to debugging and rendering performance, and that is in terms of having content and then missing a few frames, and then having content again, and that's we'll talk about that a little bit as well. But I want to go over rendering performance because it's one of them things that it doesn't get ignored, but there's not a huge amount of content. We talk about network performance massively, and there's a lot of content there, but render performance there's not a huge amount around. There's not many evangelists for it, and the content is quite sparse. You have to look into a lot in terms of how the vendors do certain things, so it's reading a lot of detailed documentation. And yeah, I want to try and have it so that we have a good understanding at a very at an easy level as possible, but also go into as much depth as required. When I did this, actually, when I put hello into Google, this is what came back in terms of like the Geordie translation. When somebody says all right to me, all right, I just say, yeah, how are you? So I don't think that means hello, but yeah, anyway. With regards, I actually want to introduce myself because I'm not really well known, even though I'm part of this community. I don't think I know hardly any of you. I mean, I met Martin tonight. That says it all. So I want to give a little brief introduction to me. So as Martin said, I'm Ben Cooper. I work for a large ad tech agency in Middlesbrough, which is based in Dubai, called Score, where I'm a senior front-end developer. And I've also worked for clients such as BlackBerry, The Sun, whilst working at Think, and previously, before I worked at ClickScroll, I worked at Sky in Leeds as a front-end developer. But I want to sort of go over this because I have no social presence. This is the reason probably none of you know me. If you look on Twitter, you can't even find a profile with egg of me because I'm just non-existent. So unfortunately, if you have any questions or you want to rant at me, you're probably going to have to come direct to me, which is probably worse. Or you can do it on Twitter and I'll hunt you down somehow. But yeah, if you have any questions, you'd probably have to speak directly to me or use email. Bit unfortunate, but that's the case, yeah. So tonight is going to consist of hopefully a lot of new data, a lot of new terms that you've never heard of, a lot of processes that you've never heard of, but that's good. I want to sort of try and hit them light bulb moments where a certain keyword, and then you sort of start to search that keyword, and that's how I want you to actually explore this. And it's a very in-depth topic, so it's hard for me to give a presentation on this topic, but it's also going to be very hard on you guys to actually take this in if you're quite new to rendering performance, because there's a lot going on. There is browser internals, so I apologise, but I'll try and keep it as brief as possible and try to have a good amount of content for beginners and also enough content for people who have a good understanding of this, so that it's not just very amateur. I stated earlier about the word frame, and in terms of a frame, you can think of a frame as a picture. If as a basic level, it's a picture. I think of a frame as the state of a certain app, of an app at a certain point. So all of these examples up here are examples of a frame, and we're going to go over what a frame consists of in a little while. Now, who has seen these metrics before in terms of network performance? Good. A few years, that's good. So we have budgets for network performance. There was a really good article wrote in I think about 1993, so it was well before my time. But it's also wrote in a book called Usability Engineering by Jacob Nielsen. And it talks about the response time limits of people in terms of tasks. So 100 milliseconds seems instantaneous. The user's fine with that. Between 100 and 300 milliseconds, there's a slight delay, but the user's still fine. Then we go on to a second. The user's starting to change context. They're thinking about writing an email, whatever. So this is in terms of loading a page, so network performance. And then 10 seconds is really the deadline in terms of the user's still there, but they're about to leave and they may never come back. So that's the budget in terms of network performance. Now we do have a budget in terms of rendering performance, and I'll go over the small equation, if you want to put it that way, in a little bit. But who knows of something called virtual sync? Yes. So vsync on the monitor. So most monitors have a refresh rate of around 60 hertz. So we're talking about it changes with 4K, but it's mainly around 60 hertz. We'll focus on 60 hertz tonight. So with that in mind, and using the metrics that we had previously, the refresh rate is we have 60. It tries to refresh the screen 60 times per second. So in order for us to keep up with that refresh rate on an app, we have to also display that many frames in a second. So if we use that small equation of a second divided by 60, we come out with around about 16.6 milliseconds to deliver each frame. That's actually not, that's basically a lie. We have 16.6 milliseconds, but also the browser has 16.6 milliseconds. So that comes at about 12 to 8 milliseconds. You can't sort of put a pinpoint on how much it is, but you probably just want to aim for 8 milliseconds, but it's between 12 and 8 because the browser has to do some housekeeping. So we're going to go over the rendering pipeline and I would want to talk about browser internals, not in depth, hopefully not. I'm going to try and keep things as simple as possible. I'm going to try and not relate this to any specific rendering engine. Do we know of a rendering engine? We all know of a rendering engine, so with Blink, Gecko, Servo is another one, Trident, Edge HTML. So we're going to focus on the rendering engine of a browser tonight, but we're not going to focus on any one specifically. The next two slides do focus on Blink, unfortunately, but that's just because I need to get the concepts across. But with regards to the events and each task that's involved in the pipeline, the names change slightly, and I'll try and accommodate for that. But really, it all comes down to browsers have different optimizations for each event. So we have two processes. This is focused on Blink specifically. We have two processes in the browser. One is the render process, and one is the GPU process. This changes for other browsers, like Servo massively changes it. For example, I think I tried Servo the other day, and every site you render on it, it renders at like 300 or 400 frames per second, like crazy amount. They have benchmarks, they've actually put benchmarks in place because they can't get a site that actually accommodates for actually challenging their rendering engine, which is just mental. But we're not going to focus on the next generation of rendering engines tonight, really. I may involve Servo at some point, but it's going to be minimal. So basically we have the render process and the GPU process. Inside of... Did that go off? Oh, no. So inside of the render process we have, I think we have maybe between three or more threads, basically. And inside of the GPU process we have two. I'm not going to really focus on service worker or web workers tonight, so it just overly complicates things. They may be mentioned later down the line in terms of tasks, but I'm not going to really focus on them in terms of actually handing off a lot of tasks to those threads. So this is actually a diagram of what I made, which is it's a bit awful, but it'll do, of the processes. And I'm trying to highlight the pipeline here of how it's basically the anatomy of a frame and what a frame looks like. So we have a frame coming in at the top into the compositor thread. The compositor is basically the big boss. The compositor threads hands off to the other threads to do work. But the compositor, it comes into the compositor, and then the frame leaves at the GPU. And as we see, a frame is just a snapshot of an application at some point in time. Now, how this looks in the browser, once again, I'm focusing on Chrome here because it's just my choice, and I think in terms of the tooling, it's a lot better. This is what a recording looks like in terms of frames. So as you can see here, we have frames set up. There is frame timing for each sort. We have the frame time for each frame, and then we can dive into what consists of each frame. You can see the frames per second, and then we also have our processes here, and then you also have more depth of what's happening in the frame. So we're not going to focus on any debugging tonight because I think that's it's a lot bigger than this, and it probably need more of an actual workshop. But I just want to actually show what this consists of. So if you run a timeline this is the timeline for loading the page, but you can run a timeline at any point in time for watching certain animations or debugging certain animations. So the first task we're going to focus on is parsing. So the only time we focus on the network is we are now hitting the network and going to request a page. It could be anything. It could be frontendne.com. I think it's .com. So let's just focus on that. We've hit that, and now the browser. The first frame is actually hit the compositor. So the compositor now hands this off in terms of parsing to the main thread. And we all know what the main thread is in terms of, if we are JS guys, we do a lot of work on the main thread. One thing to think about is that the main thread shares we share the main thread with rendering as well. So any work that we do with JS, we do rendering on the same thread as well, which we'll go over in a little while. So in terms of parsing, this is a main thread task, and these could appear as parse HTML or parse style sheet in the timeline, or whatever tooling you're using. All tooling is pretty similar, to be honest. I prefer Chrome because I think the tooling has more features, but Firefox has great tooling, so does Safari. Edge, maybe. Yeah, but it's getting better. But yeah, so if we go straight in and actually look into the parsing flow with regards to HTML. So we're not going to go in depth with each of these steps, because things like tokenization is massive. But what I want you to think when it comes to parsing, for people who don't have a good understanding of this, is that we're just creating a multitude of trees. So we'll go through that. But basically, it does tokenization on each element in HTML. That gets passed off to something called a parse tree, which is a one-to-one mapping of the HTML that came down. It's just this sort of intermediate step. And then from the parse tree, we create the DOM, which we all know of the DOM. It provides the interface that JavaScript can actually work with. But the one thing is parsing is re-entrant. So we'll go over what that means, but as you can see, with regards to script execution, this is actually a re-entrant process. Now, we've all seen this scripts at the bottom. Who doesn't do this? I was trying to be nice. Never mind. Let's move on. Yeah. So I'll tell you why you shouldn't do this. So scripts actually block parsing. I'm going to speak directly to you, actually, because if everybody else does this, it doesn't really matter. So scripts actually block parsing, and so in terms of re-entrant, when we hit a script in the HTML, parsing blocks for that HTML, we have to make a network request, actually wait for that to come back, parse the JavaScript, and then move on. So that's what it's called by re-entrant. Yeah, I'll come to that. Yeah, I'll come to that. So yeah, that's fine. You could have said that at the start, and I wouldn't have said anything. Yeah, but where was I? Yeah, so scripts that means it's re-entrant, because we can't go on parsing because we might have a document.write, and that might actually affect the output of the trees previously. So we have to halt parsing at that point. But as you see here, we have something known as speculative parsing as well. So we can move on and look at what's also known as the look-ahead parser. There's it, and move on and actually look at certain maybe assets that are like images, any sort of JavaScript that appears in the foot, and then make them requests. As you see here, defer and async also do prevent the halting of parsing. Both are a little bit different. Defer will just allow the parsing to continue, and then defer the parsing of the actual script. Async actually fires up a new thread, and then does the parsing on a new thread, and then fires it back. So we have the DOM. We've got the HTML. If there is any CSS, third-party CSS, or if we have any inline styles, etc., we'll then create a new object model, which is known as the CSS object model. With those two, we then create something known as the render tree, or it's also known as the frame tree, I think, in Get-Go, but the terms change. And the render tree is basically taking the nodes that don't, as you can see here, it's not a great example because I didn't have a lot of space to work with. But as you can see, with the paragraph tag, we've actually went over and parsed the CSS, checked this against the HTML, and then noticed that it's displaying none, so it doesn't appear in the render tree. So, and the render tree is used for the rest of the frame. Sorry. Now we move on to another task known as layout. Sorry. The render tree actually calls another task known as recalculate styles. So you might see that in your timeline. So once once those two trees, the DOM and the CSS object model, are put together, that actually calls into the event, which is recalculate styles. Moving on from there, we then have something known as layout. So the render tree has multiple trees inside of each node. So there is more nodes inside of each node that's contained. So it's like a recursive tree. But those nodes basically tell the browser what to do in the upcoming events. So layout, we now know that we have the elements that we want to see on the page, or the frame, sorry, what are involved in this frame. So what we want to do first is we want to be able to actually layer that out onto the frame, or into the UI. So what this means is that we calculate the position and the size of each element within the frame. And this is the main thread task. So this is also referred to as reflow in Gecko once again. I don't know why they changed the terminology. It just makes it harder, but yeah, it's also known as reflow. But I've got a good example from a few years ago. Some of you may have seen this, and this is a cut down version of actually what happens. But someone created this a few years ago in terms of, it was the old Firefox page, and this is layout happening in the rendering engine. This is happening in Gecko. And as you can see, we were calculating the position and the geometry of each element, that's text nodes, and also any additional lines in that node will also be created as new nodes. And all it is basically creating a multitude of rectangles. Basically, we're not drawing anything; we're just working out the position of them. As you can see, this is recursive. It happens children first. So a parent has to recursively go through its children to work out how big that itself is, and where that's positioned. So we'll go over why this is important, but you have to think about also that DOM size matters, because layout is scoped to, a lot of the time layout is actually scoped to the document, which it's not great, but you can understand why, because it's working out the children first and has to work out that before it can actually layer itself. Now we can get around this with something called layout boundaries. Certain properties allow for this, so it means that it only layers out, it doesn't really affect the full document. SVGs, for example, like the root of SVG is a layout boundary, so an SVG won't actually affect the rest of the document when it's laying itself out, and you will see that it's not scoped to the full document. Now obviously the browser's clever, we all know that, and the browser tries to batch these changes together. It'll check when certain nodes are dirtied, when it needs a new layout, when any properties have changed for those nodes, and then it'll try and batch them either at the end, either in that frame, or it'll try and move them out across to a new frame, and then do the layout on that frame to try not to blow the budget. And this is done asynchronously. Unfortunately, there is times that we can do immediate forced layout. And this actually happens if we change the font size of the document. Because we're changing the font size of the document, it's affecting a huge amount. Or we resize the browser, that causes a layout which is immediate, because the browser can't wait and batch. It can't wait for any changes to happen. So it'll just it has to do that immediately, because other elements actually may depend on the result of that layout. So it has to do that. And then there's a lot of properties in JS that actually you can force a layout, and we'll go through how that actually works. One thing to keep in mind, as you've seen, the scope of layout is huge, so it's quite an expensive operation. We want to do it as little as possible. We have control over this. It's not something that the browser is doing on our behalf. We can actually control this. Now, as I said, layout is we can actually force layout. And it's not, we shouldn't really be doing it, but it happens. It happens a lot more than actually you would think. And it comes from reading a property and then viciously writing the property straight away. So when you read a property, the browser has to work out the geometry. If you read the property for like geometry, the browser has to basically get that geometry, but then you write it again, you're basically causing that again, because once again you've wrote it and then you have to read it again to get the actual geometry for what you've just wrote back. And that, as I say, it may depend on, like, other elements may depend on the layout. So any vicious, like, read and writes actually cause what is known as a forced synchronous layout. One thing that's worse than that is something called layout thrashing, and this happens a lot. So this happens in for loops. You could have a for loop that you basically read some geometric value of an element, and then you write it, and you do it over and over again. And this could be happening on a multitude of elements. So you could be doing this 100 times, and this absolutely kills performance because we can't deliver that 16.6 milliseconds frame budget with that happening, because it's a massive amount of work. This actually is usually built into frameworks. So if you work with frameworks, you usually don't have to deal with this at all. But some older frameworks actually have a problem with this, especially SPA frameworks, when you're pulling down certain, like building and destroying views on the fly. This happens a lot, so you do a lot of layout thrashing in that, so it's something to watch for. With regards to the amount of properties, there's a huge amount of properties that actually cause forced synchronous layout, and I've got a bit.ly link there. But the thing you want to focus on is trying to batch the iterations. So if you batch all your reads in a single frame, then on the next pattern, the next frame, you can write them. So where you're not doing that sort of horrible forced synchronous layout. There's a library that does this for you, known as FastStorm, which is written by, I think it's Wilson Page. He used to work for Mozilla. I think he works for FT Labs now. But this doesn't really work when it comes to SPA frameworks, because, so as I say, you might be building, destroying views on the fly, and because it's batching, it doesn't know that you've destroyed that view, so it's trying to batch that work. But I think somebody else created something which allows you to delay it allows you to delay the batching. So I would look into that, but I think I do remember that being a problem with regards to SPA frameworks. So we now have the document of what we want. We basically know we have the frame of what we want to. I'm going to go over it, but we want to paint onto the screen. And paint comes in. It's a two-step process. Once again, it's recursive, but it differs from layout as it actually has to. It works from the backwards. So you have to paint your parent first, then you start to paint the children because of starting context and the layering. How it actually layers elements. That's by default, but that can change based on certain properties. If you change that index, then obviously that's that in order changes, and you have to paint based on how you've actually defined in the CSS. As I said, it's a two-step process. There's two parts to painting, and I'll go over both of them. The first one is, you'll see it as paint, but it's basically a bunch of draw commands. How many of you have worked with Canvas? I presume a lot of you have worked with Canvas, or you know what Canvas is. So it's basically the API for drawing elements onto the page. It's a very similar concept. You have like methods such as fill, rect, draw text. It's just a 2D drawing context. In the case of Blink, it's known as Steer, which is it's a 2D drawing library. And then you have things like Moz2D, and I think it's Direct 2D for IE. So we have these. When the render tree was created, it creates something known as render objects inside of each node. And those render objects contain these calls that the Steer needs to execute over time to actually paint these elements on the screen. So the first is actually known as paint, and it really comes as just draw calls. Next is known as rasterized paint. Now, painting is done in the main thread, but rasterized paint can actually change. So you can think of, somebody came with a great analogy when I was speaking to them the other day, and they were saying that paint is just making, it's making a shopping list. Rasterized paint is actually doing that shopping list. It takes a lot longer, because we have to basically, so we went through them draw commands, and we are drawn into vectors, but we now have to change that to we have to actually convert that to pixels, so we have to change that into bitmaps. and that's what happens with rasterized paint. So this is done on a per layer basis, and we'll go over what layers consist of in a bit. And we'll also talk about how we can create our own layers to reduce the amount of paint, because paint is very costly, especially with rasterized paint. Rasterized paint takes a lot of time, so you want to do it as little as possible. And in terms of paint, and this is just the properties such as background color, box shadow. Certain properties actually are a lot worse than others, such as box shadow, for example. We went from a time when there was box shadow, text shadow, and then we went to flat design, and it was like awesome. But if you really understand how rendering works, Steel really it obviously do things like box shadow. It wouldn't be built in the rendering engine, but these 2D drawing libraries actually struggle to do and if you look at the benchmarks, a lot of the benchmarks consist of about hundreds of thousands of elements with huge box shadows on them, because it's really hard to paint box shadows compared to actually painting background color. So yeah, that's a good one for your designer. If designer turns up and just says, I want this with a massive box shadows, nah, not having it. Yeah, you've got actually something to go back with. So now we have our layers. So we've actually painted our layers. They're in bitmaps, and now we need to composite. This is a really cheap task. Well, I say really cheap. It's the cheapest out of the tasks that I've talked about here. It's currently done on the CPU, but it can be done on the GPU. You can do it behind a flag in Chrome. I think Chrome for iOS, Chrome for Android does this by default in the GPU, which is great, because that's what the GPU is for. But Servo just absolutely kills this. It's just mental. I think the only thing that it doesn't do with regards to compositing is text, because of its aliasing, for some reason. But if you think of the page, so if you think of the frame, a frame is split into multiple parts. So we can think of them as tiles. And there's a reason for this, which we'll go over later. So we have a multitude of tiles, where I think with Chrome is maybe about 8 or maybe 6. So we have a multitude of tiles. But basically, with compositing, we need to take the layers that we've got from rasterized paint, and then we have to actually put them together in terms of how they relate to these tiles. So once again, static context applies in any composite layers that you've created yourself, or if you have things like WebGL or Canvas or video or Flash, these are created by the browser by default as composite layers, because they do so much work to reduce the paint area. We need to put these, if they overlap with each other, or there is potentially the two tiles overlap with each other, we have to actually put these together. So that's what compositing is doing. And we can also do certain drawing commands on the compositor, which once again we'll go over later. So we now have a bunch of tiles of what we actually want in the frame. And now the only thing that we need to do is basically ship them off to the GPU. Once the GPU has them, it can actually put them together and display the frame. And that's the process of going from. That's the process of going. That's just Sam telling us to have you. That's the process of going from actually parsing the page and getting the first frame out. So I'll go over these quickly because they're not as important. But update layer tree relates to compositing. We need to basically update the layer tree to tell what the composite is going to actually put in, what layers the composite is actually going to work with. Image code is a bitch. It's really difficult. It's really intensive. But there's a new API coming out called Create Image Bitmap, which means that it gets shipped off to a compositor thread, and it's not done on the main thread. But this is part of it's part of the painting section. Evaluate script is these are just events that you'll see in the timeline. Potentially, evaluate script is as we know it. Major GC, which is garbage collection. If you do garbage collection during a frame, you're pretty much, most of the time, you're pretty much knackered in terms of actually delivering a frame, but you can't do anything about it. People have asked for having an API for garbage collection, but that's just silly. The browser knows when to do garbage collection at the best time. Why would we want an API to allow people to just abuse it? But yeah, GC is difficult to get around. Minor GC, once again, and time is flight. So these are just small events that actually happen in the timeline, and you'll see. But that is basically a very, very, very quick whistle-stop tour of the rendering pipeline and what events consist in that. We're going to break now because I'm getting forced to. But also, when we come back, we'll go over how we can apply this new knowledge, or it might be old knowledge to you, into certain performance models and actually look at how we use this on the web today. So, thank you. So I actually didn't realise how much I went on the first half of this, so I'm going to try and move it along as quick as possible. When I originally sort of brought up with these, I thought it'd be 2 20-minute slots, but supposedly the first slot was 37 minutes, so that was a bit over, just a little bit. But yeah, we'll move on. So we've went through the rendering pipeline. Now I want to go over some sort of performance models that allow you to put things in play and allow you to sort of use, try and use budgets and actually allow you to visualize what sections relate to what when it comes to actually loading a site and interacting with the site. So the original stuff that we went through, the stuff that we went through previously, sorry, that was actually getting the first frame up on the page. But as I say, we have to actually render 60 frames per second. Well, we don't have to, but that's the aim. That's the budget that we have. So we are trying to aim to actually get 60 frames per second. So this is continuous. We are doing this constantly. The browser's doing this constantly for us anyway. If we are in an idle state, so and when we start to interact with the site, we have more control over what goes into the frames and how we can actually optimize those frames. So what I want to sort of get to in terms of this is that we want to try to minimize as many tasks as possible. We went through a lot of tasks. We went through 4 or 5 tasks earlier, and we also mentioned maybe 4 or 5 extra tasks. But the aim is to get the lowest possible frame rate. Sorry, to get the lowest possible budget. To get inside that budget, sorry, we need to sort of not hit as many events in that task list, basically, because as I say, painting's very, very unperformant. Layout is once again very unperformant based on the scope of what you're actually doing in. So I wanted to go through something known as rail, and I presume that a few of you have actually heard of this. So hands up with people who have actually heard of this. Oh. Maybe not. Okay, good. Actually, we're going to learn something. So this is actually a performance model, which I think it originally came out of, once again, I'm mentioning the Chrome team, but it didn't actually come out of the normal evangelists that you associate with Chrome. It actually came out with their back-end team. It was a model that they had done when they came up with when they were looking at optimizing certain aspects of the rendering engine. And we'll go through each aspect of this acronym, but what I want to sort of get to is that it's very user focused. So each task in this is about striving to achieve a certain goal for the user. It's not focused on you as the developer. We just have budgets in these tasks. It's very much user focused. So this will really help in terms of trying to sell this to people internally as well. One thing I actually want to say about this, and it's mentioned a lot, is that this is actually, in terms of the order of how this works, it's actually linear. So we're going to go through it in terms of the order of actually how these actually occur. But the reason it's real is obviously because if you name something liar, then it just doesn't look good. So they named it real. So yeah. Now I want to give you a quick example of what this actually means. So bear with me with this. I'll quickly just get something up. Okay, so I used to work for Sky. I'm not using them because I used to work for them. I actually find it's actually very unperformant. So I just want to give you an example. It's not great, but hopefully no one sees this from Sky because I was actually involved in this. But yeah, yeah. What can I say? So I just want to give you an understanding of when these actual aspects of that performance model occur. So if we go, where is my mouse? Oh, that was there. Okay, so if we go to the page, boom, that's load. That's the L of this real model. So we don't load. Now we're in idle state. So that's I. If we move and start to scroll, that's known as animation. So once again, but if we click, that's a response to a certain interaction. Then there's a load, and then there's an animation. Once again, if I click, response, and animation. So these are the certain things that happen. And we've got budgets for each of these interactions. So I just wanted to give you an example of what this actually consists of, because I don't want to go through like I did in the first half and just say what these parts are. I actually want to give you a visual example of how this actually happens. So let's move back. Okay, so we're going to go over load first. And if we go back to the metrics that I mentioned earlier, we have it was stated in the article from Jacob Nielsen that 1 second was our limit. We had to focus on actually getting to get the user's attention. We have to focus on 1 second. So you'll see this a lot in terms of network performance, and I'm not really going to cover load too much because it doesn't really impact rendering performance a huge amount. But all I can really mention in this is looking at your critical rendering path, trying to only push down what you need for that initial frame. And because all of the subsequent events actually depend on the size of the DOM tree, believe it or not, and also depend on the size of the CSS. If you have CSS selector matching, even though people see it means nothing, it actually means quite a big deal in terms of rendering, because we have to match that to the DOM and then create the render tree from that. We're doing certain invalidations, so we have to actually be careful with that. And our focus here is to get 1 second. This is more network related, so I'm just going to skip over it. But I would really just focus on the critical rendering path for load. Now, idle's an interesting one. So if we go over what we spoke about earlier, we have 100 milliseconds. 100 milliseconds is considered instantaneous. So as you see, if I click on something, I want something to happen after 100 milliseconds, and that's what we're aiming for. But in idle state, we're not doing anything. The browser's not doing anything. The browser's basically just displaying frames from the GPU and just from the cache, basically. So the browser's doing nothing. So what we can do here is we can actually look at doing certain tasks that we would normally do on the main thread that usually block in this idle state. And people try this a lot. People have actually tried this a lot in terms of actually using certain, like trying to set timeouts and just trying to listen for like a state where there's no scrolling happening anymore. We can go ahead and try and do this. But because we have this 100 milliseconds, we only have these chunks of 50 milliseconds really to actually do any work. This is what we need to aim for. If a user interacts again, we can't actually go over that. We need to achieve that 100 millisecond. We need to try and achieve that anyway. So if we do anything more than what's required in that idle state of 50 milliseconds, then we actually might, if a user starts to interact and starts to scroll again or actually taps on a button, then we actually might incur some sort of jank. Yeah, so in this state, we do actually have, so the main things that people do in this is they usually try to beat and back any analytics, or we try to load in, maybe you'll try to load in some sort of comments if you don't want to do that sort of load time. But as I say, you need to sort of stick inside of that 50 milliseconds. A response, responding to a UI, something in UI is quite quick, so we've got a lot of time to work with. So in terms of responding to a gesture or responding to a click, it's very quick. So we've got quite a lot of time in that 100 millisecond, but we really want to focus towards 50 milliseconds. And there's an API known as request idle callback, which it's a new API that's been added, and I think Firefox, Chrome support it. IE under consideration. Safari and the new IE completely useless when it comes to doing things. So and what that does is it means that we can focus on the browser will optimize this and actually allow you to run certain things at the end of the frame, or if it has any sort of if the work's not happening on the frame, we can actually run these callbacks. So if we can run certain things in these callbacks, and it provides like a deadline object, which basically says, right, you've got this deadline. If you go over this, then you maybe drop frames, or you maybe actually push the frame out to being longer than the 16 milliseconds that we're aiming for. But you can actually basically check that deadline and say, right, if this task takes longer than that, we'll just return. So maybe look into that, because that's actually really useful. It's been really useful for me recently in terms of actually doing things like any sort of, if I need to beat and back any analytics, I do it in these request idle callbacks. So it's really useful, and it doesn't block. Now, animation's a big one. Understand, this is where we need to focus on the 60 frames per second. In a lot of the other cases, so load, you're not going to really probably hit the 60 frames per second, because you're doing so much initially to get everything down. So it's not really a focus to actually hit the 60 frames per second at that point. But it's when you have motion happening, and I don't actually think this is actually, I think motion's actually a better word for this, because animation, I don't really associate any scrolling with animation. It's a motion, but it actually falls underneath this. But basically, we have, as I say, we have that 8 to 12 milliseconds to actually do this work. But when it comes to animations, you really need to understand that you want to do as little work as possible. So you don't want to do much layout, because it occurs a lot of work. You try to do as little paint as possible. So we need to really try and do just compositing. So it is possible to do this. And what we can do is, so for example, Canvas, WebGL, a lot of that, it still do paint, but sometimes it is possible just to composite those layers. So you're not doing actually a lot of work. So the frame rate's it's quite high. But to reduce our paint areas, we can actually create our own composite layers. Now, who's ever seen Translate Z 0? It's awful. It is a hack. It's a complete hack. But do we know why it's a hack? Does anybody do it? Not particularly.
It actually uses GPU 3D rendering, direct draw technique for not doing anything.
Yeah. So basically, you can create your own composite layer. It's a way of being able to allow the user to create their own composite layer. So it means that you're not painting inside the scope of the document. You're only painting inside of the scope of the composite layer that you've created. It's a hack, but it's because the reason it's still around is because of the support of that compared to the new feature, which is will change. So if you want to create composite layers, you would really go around actually using this will change transform, which allows the browser to optimize, and actually it doesn't create a composite layer up front. It actually waits for any changes, obviously, to transform on that sort of element, and then it'll create a composite layer based on the changes. So any animation that occurs will then sort of create its own composite layer. And it means that depending on the properties that you change, you can actually just do composite, and you don't do any paint, or you don't do any sort of layout, depending on the properties, which those properties are just opacity and transform at the moment. The reason for that is that you can use certain OpenGL shaders and certain calls on the compositor to just do that work directly on the compositor. You don't have to do it on a compositor thread. It can be done on the GPU directly. So the focus is to actually create your own layers if you're doing a lot of paint work, so mainly animations, in your own compositor layer. One of the things here, though, is a lot of people go over the top and just create a huge amount of composite layers for everything. You got to understand that when you create a composite layer, all the children also become composite layers. So you're creating a huge amount of composite layers if you just use it willy-nilly and you're not really understanding what it's used for. So obviously these layers are stored in the GPU, so there's also memory usage as well, and that GPU is split across all tabs that you currently use. So you have to really watch what you're doing. Don't don't go over the top with it. Understand what you're using it for. Now, if you can't actually go about just using transform and opacity, because I understand why a lot of people that I talk to, when I say, oh, just try and use transform and opacity, people are like, well, obviously I can't because I have to support like certain browsers. Transform isn't supported in many browsers, and it's obviously only 2 properties. It allows you to do a lot, but it's only 2 properties, and maybe there's a time when you actually need to use other different types of properties. So another model which was created by Paul Lewis was something known as flip, which is first, last, invert, player. So this is a performance model for animation specifically, and how this works is that he's basing it on the fact that you've got 100 milliseconds to respond, and if you think about it, most animations occur based on an interaction. So if that's maybe scroll or you're clicking on a button and a certain animation happens based on that, then you can do the work inside of that 100 millisecond barrier to get the first position of the animation, the last position of the animation, invert it to get how you're going to get to that last position, and then just play it through. So this actually works quite well with properties that you don't, so properties that are not just compositing, so opacity, transform. And this is, it's actually recommended that you use this in terms of that. But there's a really good article that explains it a lot better than I do on that bit.ly link, and the slides will be available after this. Now, this will make a lot more sense. I actually thought this was funny when I actually done it. I laughed myself. But yeah, so response in terms. So when we think about tapping on links, who remembers a few years ago in iOS that when you used to tap on a link, you used to take a little bit of a while before it actually done the next action. So we all remember that, don't we? Yeah. So the reason for that was that iOS was waiting for a second tap. It gave you a 300. That was only 300 milliseconds delay. Everybody noticed it, so it shows that those response times actually work. But that's because it's waiting for a second tap to actually zoom in. It's fixed now, so it got fixed in iOS. It got fixed in iOS 8, I think. But then there's still browsers that use UI web view instead of, is it WK web view? Maybe. So like Opera Mini, it still occurs in that. And you can fix that with having just a viewport tag in. So obviously, if you have a viewport meta tag in your HTML, it means that you're trying to deliver like responsive site. So you don't particularly need that double click like delay. If you need it, then it's still there, but it just won't occur that delay of 300 milliseconds when you actually do a single click. And we have 100 milliseconds to respond to any sort of interactions. So this is mainly focused on clicking links and actually clicking on elements that respond to that we provide in animation. So that's the barrier that we have in terms of that. And you can actually time this with console to time, because console to time actually turns up in in Chrome anyway. It turns up in your timeline, so you can actually see when your console time logs are actually happening in terms of with regards to the frames. So there's 100 milliseconds in terms of how long we've got to respond. Now, when an interaction comes through, the compositor, as I say, the compositor is the big guy. He basically I'm saying that he as if it's a person. The compositor deals with any sort of thing that comes, and the first thing in terms of it basically an interaction that comes in, that's what starts the frame. So the compositor deals with this, and it will usually deal with this. So if it's a scroll event, it'll deal with it by providing, it'll paint the new tiles in, but then it'll use the cache tiles to move the content up. But what the compositor also has to do is check the main thread and see if there's a prevent default on that event that comes in. So the compositor will do its work and try to actually provide that really snappy experience and just push everything to the compositor. But it has to go back to the main thread and check, do we actually have a prevent default on this actual event that's occurring? So if it gets pushed and then if that happens, it gets pushed to the main thread and then JS occurs, and then we go through various different stages of the timeline. So that's just to sort of give you an example of what happens in terms of the start of the frame. Now, everybody who hears this Rail model, and there's a lot more content online with regards to Rail. I've tried to move through it as quickly as possible because I've got 31 seconds left, which I'm definitely going to go over again, so I've got 4 slides left. But everybody thinks that all of those are actually weighted at the same level, so response, animation, idle, load, are all weighted. You have to basically hit every single one. But I've said that you have to aim for 60 frames per second, and I still stand by that. But if you can't aim for it, then be consistent. So try and aim for 40 frames per second consistently. It won't be a great experience, but it's better than dropping from 60 to 20 to 40, and then you'll see like you're dropping frames. So you have to aim for a consistent nature, and they're not all weighted the same because it depends on the context of what you're working with. So a content side, you'll want. I'll just turn this off. So a content side, you mainly focus on load. So you want the page to load quickly, and then it comes down to responding to the user and responding to the user's gestures and the animation of actually being able to just display the content and scroll. You don't really do much else. But for example, a spa is different. You maybe if you're transitioning between different routes, then you're not really working with a load event. You're working with a respond and animation. So all of these things differ depending on what sort of context you work in. So don't sort of take these times as gospel, because they change with whatever project you work on. And I would say aim for consistency more than just aim for what these are. So I'm sort of near the end now, and I was thinking about this when I first put this together, of actually putting sort of resources in, but I don't think it's really a good thing to do. I can't say that this resource is the best thing to read. I'm like you, really. I'm learning this as I go. For this talk, I've been sitting in Chromium blogs, trying to understand the rendering engine and reading about Servo, and I don't even understand what the hell Rust is. So supposedly it's a language, but yeah, I'm reading things that are quite intensive, but I would actually just recommend that you go and explore. I've said a lot of buzzwords, and hopefully people have picked up on those. And I think the best way to go about this is actually just going and exploring those buzzwords. There's not a huge amount of content out there, but you'll get driven down certain routes that surprise you. Like, it'll be some things that are so intense, but you'll just learn something. Like I don't consider myself a strong engineer I don't have a strong engineering background, but some of the things I've learned this week in terms of understanding Chromium and understanding Blink has been eye-opening in terms of trying to understand rendering. So I would say go and explore. Don't know what's happening. I would also say go and educate. When it comes to design, there's a big thing around designing for performance, but that's usually very network related. No one really brings in a lot of rendering into that sort of conversation. Laura Hogan and Yesenia Perez do some great work on this, but there's not a huge amount in terms of how to design for performance with rendering in mind. So it's a case of trying to go and educate your designers now. I mean, maybe you need more understanding of this, a better understanding of this, but this is really, really important. Someone asked me, someone didn't ask me, sorry. Someone mentioned at industry conference what makes a front-end developer. And it's really the browser is your environment. If anything in that environment affects you, that's what makes a front-end developer. And this really does affect you. You might not think that you'd have to deal with rendering performance, and you probably won't most of the time, but there will be a time when you do, and it benefits you to understand what's actually going on in the timeline, and understanding what is happening with the rendering engine. Obviously, as I've said this, but context is definitely key. You need to pick your battles, really. You can't just say that I'm going to focus on 60 frames per second and hitting these real budgets, because sometimes it's just not possible. For example, The Guardian, they had an issue, maybe I think it was a few months, or maybe it might be a few years actually, with regards to ad providers. You can't really do so there was an ad provider that was doing a lot of layout thrashing that was it was basically contributing to their performance. They couldn't do much about it, but it's making a decision to see if that advertiser actually provides you with enough revenue to actually see this is in terms of what you're losing in terms of the performance. So, I mean, it's a context thing. So, these are not gospel. These are just budgets that some clever people have came up with. But it's trying to aim for them and use them as a starting point, basically. And that's what I would say. And then they'll change based on the context of what you're working in. I'm going to wrap up any second now. Any second. Yeah, but as I say, this is a massively complex subject. Hopefully, I've done it some justice tonight and actually provided some sort of good resources. But I'm very much like you. I'm still learning this, so I would say go away, explore, and let me know if you have any questions, both now and in the pub, and we can talk through it, learn together. So, thank you.